Hi there, folks. Today we're going to be talking about the last bit of our material for the remainder of the year. We're going to be discussing collision theory, energy profile curves, and thermochemical equations. Okay, they're all interrelated to each other, and it's building off of what we've talked about with chemical reactions, energy, as well as looking at how it is that we can express energy through stoichiometry. Okay. So one thing I want to talk about is this idea of the collision theory. Now, just in a brief little review, a theory is nothing more than what we know at this time based upon evidence that has been collected. Theories change, okay? And so right now, the way they think that chemical reactions occur is that literally the molecules collide with each other. And when they collide, provided they have enough kinetic energy and they collide with the appropriate orientation, we will actually form something such as a product. Okay, so if you notice my diagram here, I have what appears to be two white spheres, two sets of them colliding with two orange spheres, and they collide with an appropriate orientation as well as energy. That's what's shown with kind of the what appears to be looks like an explosion kind of thing. And you notice that we actually get a product. But sometimes when atoms or molecules collide, they don't always collide appropriately, so we end up with the same stuff we started with, okay? So the things we can control are typically kinetic energy, but we cannot control the orientation, all right? So what is this amount of energy that we're talking about? Well, what we're talking about is what is called activation energy, okay? It's the minimum amount of energy for a reaction to occur. And you'll see on the diagram here on the right-hand side that I like to think of it as like a roller coaster. So if, for example, you're on the roller coaster and let's say, for example, that you're only able to get up to here with the energy. Well, because you have that much energy and that's it and that's where it occurred, you're going to end up not forming any type of product. You're going to end up forming as a reactant. Okay? But if you have enough energy and you get all the way to the peak, there's the potential that you will actually form into a product. And you're going, well, why does it take energy to get a chemical reaction going? Well, because the thing is, you've got to be able to basically break those bonds initially. And when you break those bonds initially, now new bonds can form. And depending upon what new bonds are formed will determine whether the reaction is, and yeah, I'm going to use some terms you've heard before, exothermic or endothermic. Yeah, you're like, wait a second, endo, all the way back to the beginning in January? Yes, we're literally coming full circle here, folks, okay? So let's talk about these things called energy diagrams, okay? All I'm asking you to do is be able to interpret, and they're focused on energy. I want you to be able to interpret these diagrams to see what it is that they're showing. And so the purpose of energy diagrams literally is to show the flow and distribution in a chemical reaction going from reactants to products. And we can get a bunch of key things from this. We can get the activation energy. We can actually figure out exactly what it is. We can figure out whether the reaction is endo or exothermic. We can look at it to know what the activated complex is, meaning the point at which the bonds are breaking apart and now we've got new bonds forming to where we can form product. And we can actually figure out how much energy the reactants are starting with and how much energy the products end with, okay? So when I'm talking about an energy diagram, and this should look vaguely familiar to what you just saw previously, is I want you to be able to interpret this and what this is saying, okay? So first thing first, reactants are always found on the left-hand side. Always on the left-hand side on that flat part. And products are always found on the right-hand side. You will notice that there's a peak, and that peak is where we have the activated complex. That's the part at which the bonds are starting to break, meaning that the atoms are starting to pull away from each other. And when they do, we end up making it so that we can form new bonds, okay? But the other things that we can have here is we can also look and figure out what the activation energy is. That usually is from reactants up to the peak of the graph. That would be the activation energy in the forward direction of a chemical reaction. And there's actually activation energy going in the reverse, meaning going from the energy from the products up to the peak of the graph. Now, how do you know if a chemical reaction is endo or exothermic. Okay? So the way you compare is by reactants and products. So if we look right here, our reactants are starting at 200 kilojoules of energy. 200 kilojoules of energy is what our reactants are starting with. But if you look at our products are ending up at 300 kilojoules. Would you agree, I'm hoping, that the products have gained energy compared to the reactants? And that's exactly what it is. If it's absorbed energy, then this would be endothermic. Okay? And we can actually figure out exactly how much endothermic energy it has absorbed. We would take the difference between the reactant energy and the product energy, which would be a value of 100 kilojoules of energy. Okay? So I'm going to show you a series of different graphs. I'm going to have you try and figure out what each answer would be here. Okay? And I'm going to go through them with you. All right? But like I said, there's a ton of information when you get this. Now, a couple things I do want to point out. Notice that this says the course of the reaction is going in the forward direction, meaning reactants to products. There are some chemical reactions that are reversible, that can go from products to reactants, okay? And so the energy shifts, okay? So we can actually have it where a reaction will go from reactants to products and products to reactants simultaneously, all right? But these are the big key pieces of information that I want us to be able to extract out of it. All right, so let's move on to our next slide here. So again, in an energy diagram, you can tell whether a reaction is endothermic, exothermic, the amount of activation energy required in both the forward and the reverse direction, and the amount of energy released or gained in a chemical reaction. Okay, whether that be forward or reverse. All right, so here it is. I'm going to show you a graph. And then I've got a couple questions that are going to pop up, and I'm going to go ahead and help answer these for you. Okay, so try answering the question. The first one is, how much energy does it take to activate the chemical reaction in the forward direction? I'm asking, what is the activation energy going in the forward direction, meaning forward? Whoa, hey, didn't want that question to show up there. Let's back it up. There we go. All right, so in the forward, that means we're going from reactants to products. So reactants up to the peak of the graph. So if I look at that and I go, oh, that's at 300 for the reactants, and the activation energy appears to be at about, this looks like about 350 kilojoules. So I would say that the activation energy would actually be 50 kilojoules. Make sense how I got that? Okay. Let's try the next question here. Is this reaction exo or endothermic? Okay, so let's compare. We compare the reactants and where they're starting out energy-wise, which is 300 kilojoules, and we look at our products and its energy, and it went to 200. So if the reactants are starting up here, and the products are now down here, would you agree that the products have lost energy compared to where they began as reactants? And that means that this is an exothermic reaction, okay? It's losing energy, all right? So the next big question I could potentially ask is, how much energy is released or absorbed in the chemical reactions? Because we said this is exothermic, that means it's losing energy, negative, losing, okay? So if we compare the reactants, again, to the products here, we can see that it's a difference of 100 kilojoules, which means that this is releasing, so we would put negative 100 kilojoules for the answer, all right? Negative because it's losing energy. Exo means losing. Endo means gaining or absorbing, okay? Think exosuit is on the outside. Endoskeleton is on the inside, okay? Let's try another question here. Let's go to, how much energy do the products have after the chemical reaction? Well, after the chemical reaction, I'm looking at it and I'm going, oh, products are here. It's at 200. So I would say 200 kilojoules, all right? And then the next one asks, how much energy do the reactants start with before the chemical reaction? Well, if we look at the reactants, they started at, they started at 300 kilojoules, so this would be 300 kilojoules. Make sense? I'm hoping this is making sense. Okay, let's try another one. You're going to notice that the graphs have less and less information. All right, so let's try another one. How much energy does it take to activate the chemical reaction in the forward direction? Forward, again, forward direction. Okay, so reactants up to the products here. We're starting at 100, going to 400. Your answer should be 300 kilojoules. Okay, 300 kilojoules. Is this reaction exo or endothermic? I'm hoping that you recognize that the reactants are starting at 100, but the products are at 150 kilojoules, or sorry, 250 kilojoules. This would be an endothermic reaction. It's absorbing the energy. Okay, it's not releasing, it's absorbing. All right, and so how much energy is released or absorbed in the chemical reaction? Well, if it's absorbing, we've got to compare the reactants and the products here. Okay, if the products are at 250 and the reactants are at 100, this would be a positive 150 kilojoules that's absorbed. All right, it's absorbed. Our next question would be, how much energy do the products have after the chemical reaction? Well, I would say 250 kilojoules. And then how much energy do the reactants start with before the chemical reaction? I would say 100 kilojoules. I'm hoping that makes sense, okay? Because what we're going to do is we're going to build off of this. Notice, I didn't tell you what the reactants were. I didn't tell you what the products were. I'm just giving you graphs to interpret, okay? So let's look at it with actual information on it, what are called thermochemical equations. Take a moment to look at this graph on the right-hand side. I hope you recognize that this graph, ladies and gentlemen, looks vaguely familiar. Yes, we literally just went over them, except you notice that there are some major differences here. I'm giving you the reactants. I'm giving you the products. This right here is the reactant, and these right here are the products. And you notice here that we have an 800 kilojoule value there. That, ladies and gentlemen, is telling us that this chemical reaction here is releasing or absorbing this amount of energy. We're comparing the reactants to the products. And I'm hoping that you recognize that this chemical reaction I'm showing you right here is exothermic. Okay, this is exothermic. It is releasing energy. Okay. And so, with this, ladies and gentlemen, we can actually write what is referred to as a thermochemical equation. You're like, my gosh, we've done stoichiometry, now we got these words like thermochemical equation. Think about it. Thermo is describing heat. You've been able to write chemical equations. You can balance chemical equations. All we're doing is we're taking this and we're going to write it into, ladies and gentlemen, a chemical equation with energy represented in it. So remember this diagram. This, again, remember, this is an exothermic reaction, okay? And so we're going to take a look at this. And what we can do is we can actually, from this profile curve, I can write a balanced equation. And I'm hoping you recognize, again, that this right here, ladies and gentlemen, these are the reactants, and these are the products, okay? And the idea is I can take this and actually write a chemical equation from it. C4 plus CH4 plus 2O2, which I got from right here, forms CO2 and H2O. And I'm hoping you recognize that this is balanced because I got the end product right there. Now, this is a chemical equation. What I want you to write is a thermochemical equation. Thermo meaning we're putting in the energy. I just told you that this reaction is exothermic. And because it is exothermic, that means it's losing energy. How do I know it's exothermic? Again, The reactants started with more energy than the products. The reactants had more energy than the products. How much more energy? 800 kilojoules. So when we write our equation, ladies and gentlemen, what we're going to do here is put in the energy. And you're like, well, how did you know to put it over there on that side? How did you know that it was supposed to go on the product side? Because that means that the energy is being released. It's being released to the environment. Meaning, if I sat next to this chemical reaction, it's going to feel hot to me. Now, what does this allow us to do? This allows us to actually be able to determine how much energy will be produced or absorbed in a chemical reaction. We're going to use this thing called, stoichiometry in order to do this. Okay? So, here's literally the equation I just copied from the previous slide. I hope that this, ladies and gentlemen, looks familiar. If not, reverse, take a look, compare. The question is right here. How much energy will be released when 8 moles of methane, CH4, is combusted with oxygen? How much energy will be released? And we got that released. Well, according to this, I'm hoping you recognize that for every 1 mole of CH4, I will release 800 kilojoules of energy. So the way that we start a problem like this is we start with our moles. We start with our 8 moles of CH4. Now, according to the balanced equation, for every 1 mole of CH4, I'm getting this from the balanced equation, there will be 800 kilojoules of energy released. To show that it's being released, here's the key, we got to make this negative. You're going, why negative? Why do we have to put it as negative? Because we're losing energy. It's negative. So if you do the math, the moles of CH4 cancel out. We end up with a value of negative 6,400 kilojoules. This math should look vaguely familiar. Okay, this is very similar to stoichiometry. Let's try another one. Let's try one, the hardest one I could possibly give you. Okay? Oh no, sorry. Second hardest. How much energy will be released when 4 moles of O2 react with methane? Well, we're doing the same thing. If you look right here, for every 2 moles of O2, I will release 800 kilojoules. Okay? Sorry, I'm on the wrong one. So, right here, every 2 moles, 800 kilojoules. So we're going to start with our 4 moles of O2. For every 2 moles of O2, we're going to release 800 kilojoules of energy. The moles will cancel out. So it's going to be 4 times 800 divided by 2. So we end up with a value of negative 1,600 kilojoules. Okay? These problems should look vaguely familiar, okay? Here's the hardest one I can give you. Same concept, same thing we got going here. The only difference is that in this question, we are starting with 47 grams of oxygen. Why is this different? Well, if we look, our balanced equation is in moles. This is 1 mole of methane. This is 2 moles of oxygen. This is 1 mole of carbon dioxide, 2 moles of water. It's not in grams. So the first thing we have to do is convert these 47 grams of oxygen into moles of oxygen. So how do we convert grams of oxygen into moles of oxygen? You need the molar mass. To find the molar mass, you need a periodic table. So if you look in a periodic table, you notice that for every 1 mole of oxygen, there's 16 grams. So because it's O2, 32 grams of O2 for every 1 mole of oxygen. Again, ladies and gentlemen, this is the molar mass of O2 that I got from the periodic table of elements. Now that we're in mole, we can look at our balanced equation. For every 2 moles of O2, I will release 800 kilojoules. So for every 2 moles of O2, I will release 800 kilojoules of energy. Again, negative 800 because I'm releasing that. The grams of O2 will cancel out. The moles of O2 will cancel out. And when I did the math, checking my work here, I got a value of negative 587.5, and that is kilojoules of energy that would be released from it. Okay. All right. Let's try it from the beginning one more time. Okay? Totally different equation. Let's try it. Here's the first one. And here's what I suggest. Look at it, read it, try and answer it, pause the film, and then check your work. Okay? So, it says to write the thermochemical equation from the energy diagram to the left. So I'm hoping that you recognize here that this over here is the reactants, and this is the products. Reactants are always going to be on the left, products are always going to be on the right. But notice that the products are higher than the reactants. That would mean that this is an endothermic reaction. Okay? So, if I'm writing the thermochemical equation, I'm going to write it as such. BaOH2 plus 2 NH4Cl. Now, because it is endothermic, it's absorbing the energy before it reacts. So that means I'm going to put the energy, 164 kilojoules, on the left-hand side of the arrow because it's endothermic. If it was exothermic, the energy would go on the right-hand side of the arrow. And so I would write this as BaCl2 plus 2 NH3 plus 2 H2O. And now I have my thermochemical equation for the whole thing. So now we're going to use this thermochemical equation in order to answer a couple questions. Okay, so our first question is, if you begin with 2.5 moles, 2.5 moles of ammonium chloride, how much energy is released or absorbed? Well, we already know that it's going to be absorbed. Okay, I keep doing that error every single time. It's going to be absorbed. So we start with our 2.5 moles of ammonium chloride. And then we're going to use our balanced equation. For every 2 moles of ammonium chloride, I will absorb 164 kilojoules of energy. The moles will cancel out. I'll be left with an answer of positive 205 kilojoules of energy. Why positive? Because it's endothermic. Why is it not 164 kilojoules is just the answer? Because it didn't have 2 moles of it. I had 2.5 moles, slightly more. Let's try the last one. This is the hardest one I can give you. Okay? If you produce 350 grams of ammonia, how much energy is released or absorbed? Well, we've already discussed that this is going to be absorbed, ladies and gentlemen. It's going to be absorbed. So our first thing we have to do, 350 grams of ammonia. Okay, whoops, ammonia, I said. Okay, 350 grams of ammonia. First thing I have to do, I got to convert those grams of ammonia into moles of ammonia. The reason I have to do that, again, I got to look at the balanced equation. So the molar mass of ammonia, using a periodic table, 17 grams of ammonia, there's 1 mole of ammonia. That will get me into mole. And then according to my balanced equation, for every 2 moles of ammonia, I will absorb 164 kilojoules of energy. The grams of ammonia cancel out. The moles of ammonia cancel out. I'll be left with my answer in kilojoules, and I end up with a value of positive 1,688 kilojoules. Now it's your turn to practice.